Hello there, welcome to my channel on chemistry lessons. They predominantly focus on AQA A-level chemistry, but also the BTEC Applied Science chemistry sections too. So go ahead, click that subscribe button, you know you want to. Go on, I dare you to, you know you want to. Not moving on until you do. Just a joke, go on, click that button. So this lesson then focuses on BTEC Applied Science. It's lesson 3 in a series of lessons on the second assessment objective. So that might sound a bit confusing to you, but try and familiarise yourself with the specification. It makes working and revising far more straightforward if you have an understanding of the course in front of you. So for example, the specification for Unit 1A, which is the chemistry section, it's broken into 2 assessment objectives. So you need to know about structure and bonding and the applications in science. That's the first objective. There's quite a detailed list on that. And A2 is the second objective, which is production and uses of substances in relation to properties. Now, again, there's a very detailed list on that. And this is where we're up to so far. So if you followed lessons 1 and 2 so far, we've looked at the periodic table. We looked at the periods 1, 2, 3, and 4. We've looked at groups, S block, P block, D block. And we've been able to use the SPD notation, and we've also looked at the electron arrangements using the SPD notation. And the last lesson looked at the first ionization energy and the trends in first ionization energy across periods 2 to 4 and groups 1, 2, and 7. So that was lesson 2. This is lesson 3. So this video is going to focus on these last 4 bullet points here. We're going to look at the term electron affinity. We'll look at atomic radius and ionic radius. These two, you've kind of got a bit of a head start on these two. The main new things today are going to be electron affinity and electronegativity. Let's start with electron affinity then. So electron affinity. If I give you an equation similar to we did in lesson 2 when we looked at the equation for ionization energy, I'm just going to use the symbol A again, and this time the equation is represented by gaining an electron. So this time it's gaseous atoms gaining 1 mole of electrons to make 1 mole of gaseous 1- ions. So when we saw last lesson at the ionization energy, they look quite similar, but in the ionization energy, you were forming 1+ ions from gaseous atoms. This time you're forming 1 mole of gaseous 1- ions. So instead of taking electrons away, we are adding electrons. So that's what electron affinity means. So verbalize it is the energy change when 1 mole of electrons are added, can't spell anymore, can I? It's locked down, where 1 mole of electrons are added to 1 mole of gaseous, and we have to use the state, that's important, that state symbol is essential, 1 mole of gaseous atoms to form 1 mole of gaseous -1 ions. So energy change. Quite often would use the term enthalpy change instead of energy change. Okay, enthalpy change, energy change, when 1 mole of electrons are added to 1 mole of gaseous atoms to form 1 mole of gaseous 1- ions. State symbols essential. So recognize the difference there between ionization and electron affinity. Okay, so let's have a look at what factors affect this electron affinity then. Because if you recall, when we took an electron away from an atom, when we took it away, this required energy because we were breaking this bond here. We were breaking this attraction between the nucleus and the electron, and therefore ionization energies required energy. Energy was required. So with electron affinity then, this time, instead of taking an electron away, we are putting an electron on. So we're adding an electron. So what happens here is the first electron affinity, we're actually forming an attraction. So this releases energy. So this is an exothermic process. Energy is released. This process was endothermic and requires energy to remove electrons. But adding the first electron, and I'm being careful to say the first electron because in a few slides time we'll look at the second electron affinity. So the first electron affinity, a bond or an attraction is formed between the nucleus and the electron, therefore energy is released. So how can we determine how much energy is released? How can we make comparisons? Now, the stronger this attraction, the more energy is released. Just like the stronger this attraction, the more energy was needed. So it's the same factors again. We look at the nuclear charge. We will look at the radius, and we will look at the electron shielding. So just as we saw with ionization energy, if we have a bigger radius, there's more shielding, and therefore the attraction to the nucleus is less. So if the radius is bigger and the shielding is therefore bigger, that means that less energy is released. So less energy is released here. So it's less exothermic. So you'd have a smaller value. So for example, this could be minus 200. This could be minus 120. So less energy would be released in this case. Let's have a look at the periodic table then. So electron affinity, we're going to focus our attention on group 6 and group 7. So okay then, let's just focus on group 6 and group 7 of the periodic table. We're going to consider two trends here. We're going to consider the trend as we go down the group, and we will also consider the trend as we go across a period. Okay, as we go down the group, the radius increases. And also the electron shielding increases. This means that the electron affinity is less. So it's a smaller value. So the value for the first electron affinity of fluorine is more exothermic than the first electron affinity of iodine. And that is because as you go down the group, the radius increases and the electron shielding increases. Now let's look for the trend across a period. As we go across a period, the shielding, the electron shielding, remains the same or almost the same, so remains the same. The radius decreases and the nuclear charge increases. So as we go across a period, the first electron affinity becomes more exothermic. So the first electron affinity for fluorine is more exothermic than the first electron affinity of oxygen because it has a smaller radius with a bigger nuclear charge, and the shielding remains the same. That trend is true across all of those four periods. So what you're going to do next is you're going to attempt some of these questions here. So make sure you've got those trends, you've got a note of those trends as we go across a period. It becomes more exothermic because a decrease in the radius and because the nuclear charge increases. And then we have the trend down the group because as we go down the group, radius increases, shielding increases, therefore it becomes less exothermic. So it's your turn now. What you're going to do is have a look at these 5 pairs, identify if they're in the same group or the same period, and then you're going to make your prediction for which one of these has the highest first electron affinity. And when I say highest, we're going to say the most exothermic. So pause the video now and answer those 5 questions. Right, okay then. If we consider fluorine and bromine, they are both in the same group. However, fluorine is higher up the group, which means fluorine, because it has a smaller radius and less electron shielding, therefore a higher or more exothermic first electron affinity. Number 2, for the exact same reason, we're going with chlorine this time. Because if you look at the periodic table, chlorine is above bromine, which means it has a smaller radius, it has less electron shielding, and therefore a more exothermic or a higher first electron affinity. Remember, you can't answer these questions without a periodic table in front of you. You're not expected to know these off the top of your head. You are looking at a periodic table to answer these questions. So if you didn't use a periodic table, I'm suggesting you pause again and have another go. S or Se, this time I can see that sulfur is above Se in the periodic table, so I'm going to use the exact same explanation again. Sulfur, because it's got a smaller radius, it's got less electron shielding, therefore it's got the most exothermic first electron affinity out of those 2. Question number 4. Oxygen and fluorine, this time they're not in the same group, they're in the same period. And we know the trend is across a period. The further right we are, the smaller the radius, the higher the nuclear charge and the same shielding. So I'm going for fluorine because smaller radius, higher nuclear charge, the same shielding, therefore more exothermic. And the last one, chlorine and sulfur, they're in the same period. Chlorine is further to the right, which means it has a smaller radius, higher nuclear charge, same shielding, therefore more exothermic or higher first electron affinity. So have a look at what we've done so far, and we've looked at the term electron affinity. So we've got these 3 terms to look at. Atomic radius. Well, we've used this term several times already, and the trend is as you go down the periodic table, down a group, the radius increases because there are more shells and more shielding. As you go across the periodic table, so you go from left to right, the general trend is a decrease in radius. And the reason the radius decreases across the periodic table, across a period, is because they have the same shells, same number of shells, they have similar or same shielding, but the nuclear charge increases. Okay, so the trend is down the periodic table, radius increases. Make a note of this. So the radius increases because you have more shells and more shielding. When you go across a period, the radius decreases because same number of shells, similar shielding, but an increase in nuclear charge. So your turn again then. You're going to look at these pairs and you're going to identify the one that has the biggest radius and why. So again, you must have a periodic table. So pause the video, and when you're ready, unpause and see if you can identify which of these pairs have the higher or the biggest radius. Okay, looking at lithium and beryllium, they're in the same period. However, lithium is on the left of beryllium, which means lithium will have the biggest radius because they have the same number of shells, they have similar electron shielding, but lithium has a smaller nuclear charge. Or you could say beryllium has a bigger nuclear charge. Okay. Next, oxygen or sulfur. They're in the same group. As you go down the group, you've got more shells and more shielding, therefore bigger radius. Next, sodium or magnesium. Again, this one now, they're in the same period. The one on the left, which is sodium, that's to the left on the periodic table. So again, you must be looking at a periodic table to answer this. Sodium and magnesium, they have the same number of shells, have similar shielding. However, sodium has a smaller nuclear charge and therefore a bigger radius. Next, chlorine or fluorine. This time they're in the same group, and as you go down the group, the radius increases. That means that chlorine will have a bigger radius than fluorine because it's got more shells and more shielding. So again, you look at the periodic table and you identify by position, and then you explain. Next, magnesium and Sr, identify them in the periodic table. They're in the same group. Magnesium is much further down the group, which means it's got more shells, more shielding, and a bigger radius. Let's move on to electronegativity then. This may be a term you're familiar with from the covalent bonding topic. It may not, but let's remind ourselves of a covalent bond because this term is associated with covalent bonds. So we've got two atoms there, A and B, and the covalent bond is the electrostatic attraction between a shared pair of electrons and two nuclei. That was our covalent bond. Now, electronegativity is a measure of the ability that these atoms have to attract this bonding pair, because you've got three scenarios here. This bonding pair of electrons could be perfectly evenly shared, which means that A and B pull those electrons evenly. Or you could have a scenario where A is more electronegative, which means the electrons are pulled closer towards A. That would mean that A is more electronegative because it's pulling the electrons towards itself, which would give you a slightly negative charge on the A and a slightly positive charge on the B. And of course, the third scenario could be that B was more electronegative and the electrons are in fact attracted more towards the B, which becomes delta or slightly negatively charged, and leaving A slightly positively charged. So in this scenario, in the second scenario, A would be more electronegative than B. In the third scenario, B is more electronegative than A. And in the first scenario, they both have the same electronegativity. Okay, so if we try and verbalize this, it's quite a lengthy one, but electronegativity, it's the measure of the ability of an atom to attract the bonding pair of electrons in a covalent bond. So we're measuring the ability that an atom has to attract the electrons in a covalent bond. So this one, A is more electronegative because it's got more attraction to the electrons. In the third scenario, B was more electronegative because it was attracting electrons more than A. And in the first scenario, we had equal electronegativities, which meant we had an equal share. Notice the slight charges that you see as a result of a difference in electronegativity. So what factors affect it then? So let's think about this. If we've got A and B sharing electrons, what do we know about the ability to pull electrons? It's the same factors we've looked at over and over again. It's the nuclear charge, the radius, and the shielding. So it's those same three factors. If you've got a small radius with less shielding, you're going to be attractive to those electrons. If you've got a big radius and lots of shielding, you're going to be less attractive, so less electronegative. So we're going to look at the periodic table now and have a look at how we can use the position to make our predictions of electronegativity. Now, the trend is the least electronegative at the bottom left, the most electronegative all the way up here at fluorine. Fluorine is the most electronegative, francium being the least electronegative. we ignore group 8. Now that might sound confusing, but the reason we ignore group 8 is because group 8 will not form bonds. They won't form covalent bonds, therefore we can't measure their electronegativity. So as you go from left to right, electronegativity increases. As you go from bottom to top, electronegativity increases. So you're going to need your periodic table because you're going to have a go now at making some predictions. You're going to use the periodic table to predict which of those pairs are the most electronegative. So pause the video, and when you're ready, press play. With your explanations, try and use the terms radius or nuclear charge or shielding, so try and explain them. Okay then, so F or N? Well, they're both in the same period, but N is further to the right. Sorry, F is further to the right. So F is the most electronegative out of those two because they have same shielding. F is smaller and has a bigger nuclear charge. So F has a bigger nuclear charge, has a smaller radius, and they have similar shielding. So it's the same explanations, the same kind of theory we're using throughout this whole ionization energy, electron affinity, electronegativity. And electronegativity and electron affinity are very, very, very closely linked. Right, O or S. And again, O is above S. O has less shielding, has a smaller radius, therefore O is more attractive to the electrons in a covalent bond. O is more electronegative. And for the exact same reasoning, Cl and Br are in the same group. Cl has a smaller radius, less shielding, it will be more electronegative because it's more attractive to the electrons in the covalent bond. Cl and F, this time F is above Cl. It's got a smaller radius, it's got less shielding, it's going to be more attractive to that shared pair of electrons, it's more electronegative. P or Cl in the same period this time, so they have the same shielding or similar shielding. Cl will have a smaller radius and a bigger nuclear charge. So Cl has a smaller radius and a bigger nuclear charge, therefore is more attractive to the electrons in a covalent bond. It's more electronegative. And that concludes that lesson. So hopefully that was useful. Look out for the other lessons in the series. So again, look out for assessment objective 1 lessons and the rest of the lessons in the series for assessment objective 2.